because that can get very annoying. No calculator. Yeah. Okay, are you all right with that? Is that what you wanted to know?
Yeah. The part, for some reason, like the part over water, like I couldn't remember.
Right, because sometimes sometimes you have to subtract it, like when you're finding the molar mass, remember in lab, you bubbled the unknown gas into an apparatus that looks like this, except that it had the gas over here, so we bubbled it in. And you actually made this go down to here so that you knew that the pressure inside and out was the same, because the level on inside was the same as the level outside. So that meant you knew that. So in that case, you had this inverted cylinder and all the water level was all the same. So you knew that the pressure in here was the same as the atmospheric pressure, because you have the gas is pushing the same inside and out because the level is the same. So then in order to find out what was the partial pressure of the unknown gas, you had to subtract the vapor pressure of water, because there was water in there and then there was the unknown gas in there. So you had to subtract that to get the partial pressure of the unknown, so you could use this formula. So this would be the pressure of the unknown. So if you put the total pressure in there, you would have had a little bit of error, because it's not all due to the unknown gas. So that case you have to subtract it, but in this case you would have to find the total pressure, you have to add the vapor pressure of water to the vapor.
Yeah, I get it now. I didn't realize it was asking, like, it didn't like click in my head that it was total pressure in that one, and then in the other one it was just the pressure of the gas.
Right. Okay, good. I'm glad we went over a problem like this, because we haven't done one like this in a long time. Yeah. Okay. Anybody else? See what else there is in here.
Uh, 24 of the exam 1 review.
Okay. Let me go grab it. Okay, so this is problem 24 from the exam 1 review problems. Okay, so here we have a hydrocarbon. So this doesn't have anything interesting in it. It's just carbons and hydrogen. So how would you characterize this molecule? Like, is it polar? Is it non-polar? What would you say about this one?
Non-polar.
It's non-polar, right? So that means there's going to be no hydrogen bonding. There's no dipoles. In fact, if you calculate the electronegativity difference between carbon and carbon and between carbon and hydrogen, they're all 0.4 or less. So there are no polar bonds at all. Whereas in this molecule, we have, the ability to form hydrogen bonds because of this OH. So that means that if you have one, this is methanol, that would be attracted to an OH on another methanol, which is hard for me to draw, but there. And this would be a hydrogen bond. So this really has the strongest kind of intermolecular force, and this has the weakest. So when we go to fill this out, the most important force, okay, so which is the solvent? Let's say we're saying pentane as the solvent. So this solvent is on the left. So for the solvent, the interactions between the solvent molecules and other solvent molecules, all there could be would be dispersion forces. But here with methanol, there's hydrogen bonding. And if you were to then put methanol and pentane together, what would be the strongest force of interaction between those two? Seeing as, you know, pentane doesn't have any dipoles or the ability, you know, doesn't have an OH or any polar thing on it.
Yeah, just probably dispersion.
That's yeah, just dispersion. And dispersion forces are generally weak forces. So I would put that the magnitude of the interaction would be small, but I would also accept moderate, right? Because pentane is getting a little bit bigger. So it's, you know, I would accept either one. But hydrogen bonding is definitely large. And now what about the sign? So, delta H solvent, okay, so what we're talking about is breaking up the interactions between two solvent molecules. That's what delta H solvent refers to. So if you're breaking up interactions, then that's always going to cost energy. So this is going to be positive. So delta H solvent and delta H solute are always positive, because what that is referring to is pulling apart solvent molecules and pulling apart solute molecules. In other words, pulling them apart from each other. Okay. And then when you put them together, there's only dispersion forces. So that's, again, a small or moderate. Sorry, what did I do there? I circled the wrong thing. That's like small, or I guess it's easiest to understand if you thought of dispersion forces as small. That might be, you know, but I would accept, like I said, moderate as well. So what happens here now is you're releasing some energy because you're putting methanol and pentane together, and there is some interaction, but it's a weak interaction, so it's relatively small. And so the big deal here is that you had to break up these very strong hydrogen bonds that expends a lot of energy doing that, and you're not getting that energy back. So that means that overall, when you add all these contributions together, delta H solvent plus delta H solute plus delta H mixing, where these two are positive and this is negative, and this delta H solvent is relatively small. Solute is very large, takes a lot of energy to do that, but you're only getting back a smallish amount of energy. Then this overall is going to be positive, and it's going to be pretty large because it's going to be dominated. It's kind of like dominated by the fact that you're breaking up that hydrogen bonding. Okay, so delta H solution, which is the sum of these three, will be large and positive. If you have the same type of forces that are breaking up as the ones that formed, then delta H solution is around 0. But here, because you're not getting releasing the same energy that was required because of the breaking up of the hydrogen bonds. This is expected to be positive. And you would not expect methanol to dissolve in pentane, because I would say that the delta H solution is too large. Entropy can't overcome that. Entropy can overcome a small positive a delta H solution, but not a large one. And, I do realize that this is an oversimplification, a gross oversimplification in a way of what's really happening here. So I wouldn't throw an example at you that was too nuanced, if you know what I mean. It has to be pretty cut and dried, But anyway, that's what I would say there. Okay.
Yeah.
Mhm. So I'm curious, does this seem a little less strange, this kind of problem, than when
Yeah.
you saw it at the beginning of the semester? Maybe it's a little bit.
Kind
seen
of.
it a couple times. Any questions about that?
So entropy can only overcome small negative.
Well, if delta H solution is negative, then enthalpy favors the forming of a solution. Entropy always favors the forming of a solution. So, of course, it would be soluble. It's when delta H is near zero that you would say, oh, well, you're basically requiring a certain amount of energy, and then you get that energy back, it's released. So like, for example, if you had two hydrogen bonding liquids, like ethanol and methanol, or methanol and water or something, you're breaking up a lot of hydrogen bonds, but you're getting a lot of hydrogen bonds forming. Or if you have two molecules that have dipoles, but not hydrogen bonding, then you're breaking up a moderate force, you're forming the same force. So the delta H solution would be around zero. And in that case, you'd be like, well, okay, is that going to be good enough? And the answer is that entropy can, because of the second law, really, that entropy increases for a mixed up solution, the solution would form in that case when delta H is around zero. But here it's actually quite positive. But if you had a case where you circled near zero, then you would say, yes, it would dissolve, because entropy could overcome that. Entropy would win, it would take over. Enthalpy doesn't care, as if it had a mind to care.
Got it.
Yeah. Still trying to find a calculator. This office is a mess. Oh well. Get you guys to do my calculating. What else?
So delta H, it just means change in enthalpy, correct?
Sorry?
Delta H is change in enthalpy?
Yes.
Okay.
Yes. Juan, you have a question?
About vapor pressure lowering. I don't know what problem it is, but that's a problem.
Let's see. I don't know if there's an example of that, so. Trying to find a good problem. This one with the lactose is a lot of true or false, and that problem, that, I didn't like that example very, oh, here we go, here's 29. That's what we'll do, 29. Okay, here. Is there a B and a C that I don't know about? Yes, there is. Okay. So we have methanol and water. Vapor pressure. Okay, so we have that, let's get the notation correct here. When you have a little zero on top, that means for the pure substance. So the vapor pressure above pure methanol is P0M. And that is 94 torr. And P0 water at this temperature is 24 torr. And you're told that you have 50 grams of each. Okay, so what we have to do here is, realize that the equation that we're going to be using is PW, that's the vapor pressure above the solution, vapor pressure of water above the solution. And the solution I'm talking about is 50 grams water and 50 grams methanol. So, you mix them together. And we're talking about, in a closed bottle here, let's say. What is the vapor pressure above that solution of water, and PM, vapor pressure of methanol above the solution. So the equation that we're going to use is PW is XW, PW0. So this is the vapor pressure if it was above pure water times the mole fraction of water. And the same thing for methanol. So the first thing we have to do is figure out the mole fraction of methanol and the mole fraction of water. Well, that's not the first thing. First, we have to figure out the moles of each. So we have 50 grams of methanol, and methanol's molar mass is 32. So that comes out to 1.56 moles of methanol. And now we use water's molar mass. And we get 2.78 moles of water. So the mole fraction of methanol is 1.56 over the total moles. So we add them together. That's 0.36. You'll notice it's less than 1, it's a mole fraction. XW, now I could do it, I could take 2.78 over the same thing, the same total. And I would get 0.640. Or I could just instead take 1 minus 0.36 as an alternate way to do it. Okay, so the partial pressure of water is XW P0W. 0.640 times 24 torr. So that comes out to 15.4. So that's the partial pressure of water. And that of methanol is the mole fraction of methanol times the vapor pressure of methanol over the pure. So it's 0.36. Oops. So it comes out to 34 torr. So here's the thing, you have this mixture in the liquid phase. You have this mixture, 50 grams of each. And in fact, that's actually got more water in it per mole than methanol, right? So in the liquid part of it, you've got, 2.78 moles of water and a smaller amount. Okay. But in the vapor above that, even though there's less methanol in the liquid, you have a lot more methanol in the vapor. And that's because methanol is more volatile. So the more volatile component, even though it's outnumbered in the liquid, there's more water in it, the vapor is much richer in methanol, which is not surprising because, as you could see from these numbers here, these two numbers, that methanol has a much higher vapor pressure than water does over the pure. It's almost 4 times higher. So it's not surprising to see that methanol has a much higher vapor pressure here. So what about which would have the higher boiling point? So what is boiling point? Does anybody remember what boiling point is? The definition of boiling.
When when it turns to gas, basically.
No, that's not really true because, at any temperature above a liquid, even if it's nowhere near the boiling point, you have some vapor, right? So it's turning to gas all the time. It's just not boiling. So I mean, even if you have water at 25 degrees C in a closed container, there's water vapor on top of that liquid. You raise the temperature, the water vapor pressure goes up. You raise it, goes up. But boiling is very special because boiling is when the vapor pressure of water gets so high that it equals atmospheric pressure. And you see those little bubbles forming on the bottom of well, if you have a see-through pot or if you look down from the top. And what happens when boiling happens is these bubbles get big and they maintain their shape until they rise to the top and break up. And that's because when these vapor bubbles form, they're forming at a pressure that equals atmospheric pressure. And so they're able to maintain that they don't collapse, right? They don't collapse because they have this higher pressure. So boiling technically is the temperature at which the vapor pressure above a liquid equals whatever the atmospheric pressure is. So that's technically what it is, right? So it's the boiling point. It's the temperature when the vapor pressure above a liquid equals the atmospheric pressure. So at sea level, that's 1 atmosphere, or 760 millimeters. So when the vapor pressure gets up to 760 is when you see those giant bubbles. So given all that, you don't even need to know that necessarily to answer this question, but which would have the higher boiling point? So what's the answer to that? Which has the greater intermolecular forces?
Water.
Yeah, so despite the fact that methanol can form hydrogen bonds, it can't form a hydrogen bond from every atom like water can.
Yeah.
And it also has that CH3 group that's pretty nonpolar. So I guess I would say that, water has much greater intermolecular forces. I'll just say, and so it requires a higher temperature in order to get enough molecules in the gas phase that the pressure equals atmospheric pressure. I'd accept a much less detailed answer than that, It requires a higher temperature to get in the vapor phase because of the greater intermolecular forces.
So just a question.
Yeah.
So on my review sheet, I put an answer of like water has a higher boiling point because it has a lower PW0. What does
Yeah, that's this here. Water has a lower PW0.
Yeah.
That's the vapor pressure above pure water. So what we're talking about here is when you have a mixture, right?
Yeah.
But water itself has a much lower vapor pressure than methanol at the same temperature, because water is having a harder time getting into the vapor phase because it has to overcome those stronger intermolecular forces. So that's another way of saying it, saying that, the fact that this number is smaller is because water has greater intermolecular forces.
Oh yeah, because the higher the intermolecular forces, like the lower the vapor pressure is.
Yes. Because
Okay.
remember, all those things that go up with intermolecular forces, the boiling point goes up, the freezing point goes up, surface tension goes up, viscosity goes up, vapor pressure goes down.
Yeah.
Yeah. Because then you're talking about the number that's in the gas phase, and that number would be smaller if the interactions between molecules are stronger.
Got it.
Yeah. We did a lot this semester. Look at all this stuff. It's a lot of material. Yeah.
Yeah, I was getting a little overwhelmed at first.
Yeah.
I'm kind of starting to understand that. Oh yeah, I've done this already. So.
It's a good thing. It's a good thing when that happens. That's when you really learn something, Huh. Right.
Are there going to be extra credit problems on the final 2 or just the 3 parts?
Well, I made, so the last part 3 is 6 out of 12. They're like some multiple choice, some, they're short problems. They're not many parts. They're just like asking one thing. And they're 5 points each. And I'm letting you do 2 extra ones for extra credit.
Okay.
But I'm not necessarily going to give 10 points of extra credit, probably just 5. But
Okay.
yeah, so you'll have to tell me which ones you pick. But no, I definitely put that in there. Yeah. Mm.
Number 27.
Oh, okay.
No idea what to do.
Wait, I got the wrong thing. Wait, oh, this is exam 1, right? Review, yeah, okay.
Yeah, the first one. I know the rest is fine.
Oh, yeah. Good, let's do this one. '97. The solution is prepared by dissolving 9 grams of glucose in 250 grams of water. Okay, so first of all, let me go grab the equations from this review sheet. So we could take a look at it. Maybe something will strike you as familiar. Let's see. Actually, we really just need, let's just take this. I'll grab this too in case we do a problem like that later. Okay. So a solution is prepared by dissolving 9 grams of glucose in 250 grams of water. Tells you the molar mass of glucose. It asks for the molality. Oh, gee, is molality on there? Yeah, I think I should put it on there. I already made copies. I'll have to write it down at the beginning of the test, okay? Somebody remind me. Because I think that's something I might have given you, but it's not on this sheet for some reason. So molality. Anybody remember what that is? Oops. Okay. So I'm going to give this equation to you. I don't see it on there. I wonder if it's on the actual sheet that I have to look that up. Oh, no, here it is. It's right here. Look. See? Tell me you see this. You see
Yeah.
that? Yeah,
Yep.
so, okay, so molality is there. So, okay, so what is the molality? So you should be able to figure that out. Even if you didn't know how to do this problem, you should be able to figure that out. So 9 grams of glucose. You have to know the molar mass, but they give it to you. So that comes out to 0.050 moles of glucose. Okay. The freezing point of this solution is negative 0.372 degrees C. Okay. So now if you look at these equations, so what it's asking, what is the value of the freezing point depression? So look, the freezing point depression is the freezing point of the pure solvent, 0, minus 0.372. In other words, it's the positive, it's the absolute value because the freezing point of water is 0 degrees, whatever the freezing point is for the solution, the negative of that is what we call the freezing point depression, the delta TF. Okay. So far, I don't think it's too hard. So use your answer to A, which was the molality, and this equation to find the freezing point depression constant for water. So we know that delta TF is I KFM. Now, what's this I? So it doesn't say here what the I is, but there's an I down here. It says for ionic compounds. You remember what it means, this I? So if you have like NaCl and you put that in solution, you get 2 particles. So I is equal to 2. It's basically the number of particles per formula unit. You know, if you have MgCl2, this I would be 3 because you get Mg2 plus and 2 Cl minus. So you add the particles up, you get 3 particles. So I equals 3. But what is glucose? Is glucose an ionic compound? What's the formula of glucose?
C6H12. I forgot the rest of it.
Okay, it's not an ionic compound. It's
Yeah.
it's molecular. So I is equal to 1. So you don't even have to worry about the I when you have a molecular compound. So what are we trying to do here? Oh yeah, so we'll take the delta TF. We'll use this equation, delta TF is IKFM, but I is equal to 1, so we get rid of it. So just take that delta TF, which was 0.372, divided by 0.05. Wait a minute. Oh, we never found the molality. That was just the moles we found. Okay, so see, we didn't get to the molality because we had to divide that. So it's 0.050 moles. So it said it was 250 grams. So we have to make that kilograms. And this comes out to 0.200 or 20 molal, which is just 0.20 little m. So now we go down here and we take the delta TF divided by that 0.20. And it comes out to, well, in 2 sig figs, it's 1.9. So that's the K. It's really 1.86, but that's all right. So now, are you with me, Juan? You're okay? Are you following? It's okay?
Yes, it's fine.
Okay, so given the fact that now we know what the K is, what would you expect the freezing point of a 0.2 molal solution of aluminum chloride to be? Okay, so if we think about AlCl3, you know, we know delta TF is going to be IKFM. Okay, but now what is I here? How many particles do you get
4.
from one? How many?
4,
4.
because you had like AL 3+ and then 3 CL minuses.
That's right. So that's 4 times KF times 0.2. That's the molality. I'm just using the 1.86 because I know that's what I did here. And I don't have a calculator, so I have to use. And so that comes out to 1.49 degrees C. So the TF, so that the freezing point is not 1.49. The freezing point would be negative 1.49, right? Because freezing point is depressed by a solvent, so it goes below 0 by that much. And so this would be the answer for the 0.2 molal AlCl3. And then it asks, what would the freezing point of a 0.4 molal sucrose solution be? Okay, so this is sucrose, which is another molecular compound. So it would just be, the I would be 1. So delta TF would be 1 times KF times 0.2. So it would just be twice what it was for glucose. So the delta TF would be 0.7, but the freezing point would actually be negative 0.7 because it's depressed below 0 by that much, because 0 is the freezing point of the pure liquid. That makes sense? It does feel a little old, like ancient history.
So the freezing point is negative 0.744 degrees Celsius.
Yes.
Okay, good.
Yeah.
Yeah, it's all starting to come back.
Mm-hmm. Maybe we should do 28 too.
I think 28 is fine.
Yeah.
Yeah, it just seems like same thing as nearly, well, actually not the same thing as.
Well, the thing though is you have to remember that for osmotic pressure, you have to use a molarity.
Yeah, which
And
is,
that's okay. It's clearly stated here. And I
Yeah.
don't tell you what molarity is because everybody should know what molarity is.
mole solute over liter solution, right?
What's that?
It's mole solute over liter solution.
Yep. And there's only an I if we're dealing with an ionic compound. So here, this is an enzyme. That's not an ionic compound.
Yeah. So
Yeah, this is a little backwards though, this problem. It's not just asking you what is the osmotic pressure,
yeah, actually,
telling you the osmotic pressure.
yeah, I think I want to go over it.
What you do?
Yeah.
Yeah. So, so the general equation is pi is I times the molarity times RT. And this R is, oh, wait, no, it's not. It's also liter atmospheres. You know, how did I know that? It's because, you have pressure here, which you're going to have to put into atmospheres. So this is the only unit of R that we know of that has volume and pressure in it. Doing it in joules isn't going to get you anywhere. So here, we don't even have to worry about the I, because I is equal to 1, because this is not molecular, not ionic. Okay. So what we do here is we figure out what the molarity is by taking the given pressure. We would have to convert it to atmospheres and dividing it by RT, because T is given as well over here. We have to convert it to Kelvin. So let's do that. So R, we know, I already wrote that down. So T is 27 degrees C, which is 300 Kelvin. The osmotic pressure is given as 33.7 torr. So we would have to convert that to atmospheres. I'm waiting.
That
Right,
Point
so
zero.
it comes out to,
0.0443
yep,
ATM.
so 0.0443 ATM over temperature is 300. So you could see that with using, so you could see the unit is going to be moles per liter. It's going to be the inverse because this is in the denominator. So it's going to have the right unit. It's going to be molar. And it comes out to 1.80 times 10 to the -3 molar. And so that's 1.80 times 10 to the -3 moles per liter. But we were told that this is 100 milliliters. So this is 1.80 times 10 to the -4 moles. And you're given the mass. So the molar mass is 4.50 grams over this number of moles. And it's a big molar mass because it's a protein. $25,000. So that's a difficult kind of osmotic pressure problem. You could also be asked, what is the osmotic pressure if, you know, be given the amount of grams and the volume and you calculate the molarity. So anyway, that's how you do that problem.
One second. Sorry, I'm just having trouble like seeing the steps. I mean, I see them here. It's just like trying to think of how to like put it into practice.
Yeah, I mean, so I think first thing is to find the molarity.
Yeah.
Yeah.
Find the molar.
I think
Oh,
once you
okay.
have the molarity, you'd say, oh, what could I do next? And you'd realize you could multiply by the volume.
I see what was it confusing? I saw basically what I was thinking is that like, I don't know, if I were to do this without any help, then I would immediately put like 1.80 times 10 to the -3 as the answer, but that's molarity and I need molar mass, so I'd figure that out.
Mhm. Mhm.
Okay. Yeah, I get that.
All right. Anything else?
23.
Okay. Boy, this problem is boring. So we're heating up a sample of ice, right? So this is a long, boring problem. I guess we should do it. All right, so we have ice. We're heating it. So we're starting at -12. So when we get to 0 degrees, okay, now when you, so how am I going to illustrate this? So this heating step here, the temperature changes. When we get to 0 though, we're still going to continue to heat it, but the temperature stays at 0 degrees because this is now melting. That's what the heat goes into doing. Once it all melts, now we have, so here now we have liquid at 0 degrees. We're going to continue to heat it. Until 85 degrees. No, it's not as long as I thought. Good. So we have step one here is a step where the temperature changes. And you're heating the ice. Step 2 here is a phase change from solid to liquid. This step 3 is you're heating the liquid from 0 to 85. And the temperature is changing. So when you have temperature changes, let me grab the equations. Okay, yeah. Okay. So when you have these temperature change steps, then you use this formula. Q is MC delta T, where C is the heat capacity. And it's different for ice or for liquid water or for gaseous water. So what was the mass here? 425 grams. The heat capacity for ice is 2.09 joules per gram degree C. And then you have the change in temperature. Okay, this is going from -12 to 0. So it's 0 minus 12. It's always final minus the initial. So it's actually plus 12 here. And that comes out to 106.59 joules or So I'm gonna move the decimal point, 1, 2, 3, that's 10.7 kilojoules. Okay. And now we use a similar method here for heating the liquid. But notice this C is now for the liquid water. This is for ice. So we still have 425 grams, but now the C for liquid water is 4.18. And now what's the change in temperature? It's going from 0 degrees to 85 degrees. I'm waiting for my pen to come back. It's not coming back. So it's 85 final minus initial, which was 0. So that comes out to 151147 or 151. That's joules. This is kilojoules. You could see that heat capacity is twice as big in the liquid state. So it takes twice as much heat to heat water up the same number of degrees. And it was a lot more degrees, which is why this number here is a whole lot bigger, the 151 than the 10.7. But we also have to worry about the phase change. So notice down here, you're told the heat of fusion of water, and notice it's given in kilojoules per mole. So we have to take the number of moles of water and multiply it by 6.02 kilojoules per mole. So it was 425 grams, 18 grams per mole is 23.6 moles of water. So this is going to be 23.6 times 6.02. That's 23 point, I should put in the units really. Okay, so it comes out to 442 kilojoules. So you basically have to add these all up. Comes out to 304 kilojoules, and that's the answer. So you have to add up all the contributions.